Hey guys, so after the alien problem on the last test, I know you guys are all thinking the same thing that I am. Is everything our professors say really true? And today, I think by looking at if ice is really frictionless, we'll find out. Let's get started. So, as we're in the winter spirit right now, the purpose of this lab is to figure out if ice is truly frictionless, right? So to achieve our purpose, I'm going to be using VPython to do a simulation where obviously the surface is completely frictionless, and then analyzing a real-world scenario of the exact same principle, right? So for the initial conditions, we're going to have two people, one person 50 kilograms, the second person 75 kilograms, and they're both going to be pushing off of each other on a frictionless icy surface where we're expecting that no external forces are being applied, right? And a quick preview of the results. Not so fast, obviously. Don't want to ruin the mysterious result. But a quick disclaimer: the result is shocking. So turn back now if you want to keep trusting your professor, and give me 100 while you're at it. Anyway, the main physics ideas are Newton's second law, F equals ma, the momentum principle, the conservation of momentum, kinetics, velocity update, position update, same as most other ones. And so, a little out of order, first let's take a look at the programming. Let's look at the ideal scenario. So, quick overview. I made a computational model in Python where two people are pushing off each other, kind of like the image here, with the initial conditions and a quick velocity calculation, since velocity shouldn't change after the impulse is given, as well as a position update in the loop. And here is the video. As you can see, the less massive blue ball is moving faster than the more massive red ball, but they're both moving at a constant velocity since, well, there is no friction, right? But let's take a look at the real stuff, the real world. It's lab time, guys. So obviously, first we have to set up tracker first. I'm 6.7 meters. Obviously, I'm joking, guys. And here's the actual video where I use tracker to analyze the result. Bang. So me and my friend, we push off each other on the ice, but whoa, you guys saw that? Velocity initial was 0.87 meters, but our velocity final, 0, with a delta t of 1.27 seconds. Uh-oh. So, is ice not actually frictionless, guys? Unfortunately, yes. Using Vf equals Vi plus Fnet over m times delta t, we can solve that our coefficient of friction was actually 0.07. Guys, our professors might be frauds. All those questions with ice being frictionless, guys, it was a lie. It was never frictionless. So let's have a quick discussion. Where did we succeed today? Well, we figured out that ice isn't really frictionless, but where did we fail, guys? We also figured out that ice isn't really frictionless. How can we trust our professors now, guys? So some what ifs, and what does it mean? What if ice was really frictionless? Ideally we might have a better transportation system, kind of like the boats in Minecraft, and ice skating would also probably really suck. And what does it mean to be truly frictionless? Well, it's where something can interact with other objects and they're not losing any energy during that contact, but unfortunately, no such substance exists. So, if you guys came this far, that's a picture of me and you. We're now best friends. But so error sources are the camera movement in the video as well as the human error using tracker. And final conclusion, guys: ice in the real world, at least, is not frictionless. So I hope this new idea does not make it harder for you to go to sleep tonight. But I think it had to be done, and hopefully, on the final, we don't get another alien problem. Thank you for listening. You've been great. Have a great rest of your day.